Good afternoon. This last video will be covering typical types of rice table problems that you will encounter for non-equilibrium calculations. In order to solve these problems, we must set up a rice table. The rice table stands for R being the chemical reaction, so your balanced chemical equation. The I is your initial concentration in moles per liter. The C is your change in concentration. These will be, again, your plus X's and your minus X's. Like stoichiometry, we're using it from the balanced chemical equation. It's your coefficients. However, with the rice tables, you have to remember to check your Q versus your K to see which direction the reaction is going to progress. So unlike the stoichiometry, the C will not always be a negative for the reactants and a positive for the products. You must check the way the reaction shifts to establish equilibrium. And finally, E will be your equilibrium concentration. Okay, so our first problem here, we have a closed system initially containing 1.000 times 10 to the negative third molar H2 and 2.000 times 10 to the negative third molar I2 at 448 degrees Celsius is allowed to reach equilibrium, and at equilibrium, the HI concentration is 1.87 times 10 to the negative third molar. Calculate Kc at 448 for the reaction taking place, which is H2 plus I2 forms 2HI. The first thing that I want to tell you guys is to make sure that you stay organized in this process. Give yourself plenty of space on these problems so that you can easily follow your work, and more importantly, the AP graders can follow your work. So I'm going to rewrite the expression and the equilibrium reaction, and then we'll start to work through the problem. So the first thing I'm going to do is I'm going to set up my Kc expression, which would be the HI concentration squared divided by the H2 and the I2 concentration. Now, when you're doing your rice tables, again, give yourself plenty of space. So I'm going to rewrite this. H2 plus I2 forms 2HI. So that would be my R. For the I, if we look, we have 1.000 times 10 to the negative third molar H2. And for I2, we have 2.000 times 10 to the minus third molar for the I2. And that's all we have initially. So again, key thing, that's the initial concentration. So because those are the only two things listed, we know that the HI will be equal to 0. For my change in the coefficients, again, I have 1, 1, and 2. So I have an X, X, and 2X. Now, as I mentioned, we need to determine the direction that the reaction is going to shift to achieve equilibrium. In cases like this, where we have 0 being one of our initial concentrations, the reaction will always shift in the direction to produce some of that substance. So those are the easy ones. You don't have to actually solve for Q in this case. If we had initial concentrations for each of our reactants and products, then we'd have to solve for Q and determine which direction the reaction would move to reach equilibrium. So in this case, we know the reaction is going to shift to the right, so therefore the H2 and the I2 would both lose some of their initial concentration, and the HI would gain some of the concentration. And then finally, the last piece of this puzzle, we know that at equilibrium, my concentration of the H2 would be 1.000 times 10 to the negative third minus X. The I2 concentration would be 2.000 times 10 to the minus third minus X. And it tells us in the problem that the HI is 1.87 times 10 to the negative third. So we have the ability to solve for X using this last piece of information. So we can just set up an equation here where we have the value for X, which is going to tell us again the change in X for all of the different reactants and products. So my X, I can set that equal to 0 plus 2X equals 1.87 times 10 to the negative third. So dividing both sides by 2, I get my x value for this particular reaction being, and I'm going to cheat and keep my exponents the same, 0.395 times 10 to the negative third molar. So knowing that that is my value for x, I can then plug that into my expression. So by just putting this in, I can set my equilibrium concentration of H2 now being equal to 0.065 times 10 to the negative third, and the I2, 1.065 times 10 to the negative third, and then I have the 1.87 times 10 to the negative third for the concentration of the HI. So now as I set up my expression, I can plug those values in. So I have 1.87 times 10 to the negative third for the concentration of the HI, and I will square that. And then I can divide that by the 0.065 times 10 to the negative third and 1.065 times 10 to the negative third. And that will tell me the Kc for this reaction. So in this situation, as we plug everything in, we end up with a value of 51. This next problem is going to be dealing with a Kp problem where we'll solve for a partial pressure for the equilibrium mixture. You are looking at the Haber process, N2 plus 3H2 forming 2NH3. Kp equals 1.45 times 10 to the negative fifth at 500 degrees Celsius. In an equilibrium mixture of the three gases at 500 degrees Celsius, the partial pressure of H2 is 0.928 atmospheres, and that of N2 is 0.432 atmospheres. What is the partial pressure of the NH3 in this equilibrium mixture? Now, for this particular type of problem, we don't typically have to write out a Rice table for it because they're giving us equilibrium concentrations for 2 out of the 3 variables, and we know what the Kp is. So when we set this up, I need to just simply look at my expression. Since we're dealing with Kp, remember we're using parentheses for the partial pressure, and I have NH3 concentration squared, and I would have the partial pressure of N2 and the partial pressure of H2 quantity cubed. So as I begin the process here, I can plug in my values. So I have for the Kp 1.45 times 10 to the negative fifth, and that is going to be equal to x squared, partial pressure of the NH3, divided by the partial pressure of the N2, 0.432, and the partial pressure of the H2, 0.928 quantity cubed. So as I multiply and divide, rearrange my expression, I end up with the 1.45 times 10 to the negative fifth multiplied by 0.432 and 0.928 concentration cubed, and all of that together equals 5.01 times 10 to the negative sixth, and that is set equal to the x squared for the partial pressure of the NH3. And so I can take the square root of the entire thing, and my value for x would equal 2.24 times 10 to the negative third atmospheres for the NH3. Alright, so our next problem is going to be the toughest one that you get. For this, you're going to have to use the quadratic equation to end up solving for your value for x. If you notice in the problem, you have a 1 liter flask is filled with 1 mole of H2, 2 moles of I2 at 447 degrees Celsius. The value for the equilibrium constant Kc for this reaction at 447 448 degrees Celsius is 50.5. What are the equilibrium concentrations of H2, I2, and HI in moles per liter? So in this case, because we have exactly 1 liter for the flask, my molarity is the same as my number of moles. So once more, we have our equilibrium expression, Kc equal to HI concentration squared, H2 and I2. And that again is equal to 50.5. So I'm going to set up my rice table once more. So again, for the R, I have H2 plus I2 forming 2 HI. It tells us initially that we have 1 mole per liter and 2 moles per liter. And then we'd have 0 for the HI. So again, we know in this case, for Q, it would be shifting towards the right. So this would be minus x, and plus 2x. So there's my I, there's my C, and now for my E, I would have 2x, I would have 2.000 minus x, and I would have 1.000 minus x. So you can see in this case, because they don't give us the value for the equilibrium concentration of HI, it's going to make the process a little bit trickier for us to solve. Not impossible, but like I said, we're going to have to use a quadratic equation. So if you don't remember quadratic equation, you would have negative b plus or minus the square root of b squared minus 4ac all over 2a. So if I now go and plug in my values for Kc, we had 50.5. Set that equal to the HI concentration, which was 2x, quantity squared. And then for the bottom, we have for H2, 1.000 minus x, and for I2, 2.000 minus x. And now at this point, we can FOIL out our problem, get everything together on the same side. So if we would do that, we would have for the bottom part here, I'm just going to put 50.5, multiply it out, we've got 1 times 2, so I'd have the 2.000, and then I would have minus 3.000x, and then plus x squared. So I have that, and then I can set that equal to 2x quantity squared, which is 4x squared. So when I FOIL this out and subtract everything, I would end up with here 46.5 times x squared, again 50.5 times the 1 for the x, and then subtracting the 4 gives me the 46.5. I would have minus 151.5x plus 101.0, and we can set that all equal to 0. So to solve for my x value, remember you're going to have 2 roots for this. We have to decide which one would be the appropriate value. So if I set up to solve for x in this, I'd have a negative of the negative 151.5. That would be my b. And then I can say plus or minus the square root of negative 151.5 squared minus 4 times the a, which was 46.5, times the c, which was 101, and then we will take all of that and divide it by 2 times a, so 2 times 46.5. So my x value we have for this 2.323, or we could have 0.935. Now, in this situation, again, looking at my initial reactants and products, it is impossible for the x to equal 0.232 because of the fact that the initial concentrations were 1 and 2. So I know I can cancel that one off. Sometimes you'll get a root where 1 is positive and 1 is negative, and that makes it super easy. But in this case, you just have to look and see, because the 2.32 is larger than my initial amount. There's no way that that could be my x. So for my equilibrium concentrations, I can just plug those values in, and they should look familiar. For this, I have 1.000 minus my value for x, which again was 0.935. So that would be equal to 0.065. For the I2, I have 2.000 minus x, so that would be equal to 1.065 for the molarity. And then for the HI, that's equal to 2 times x, so we have 1.87 for the molarity of the HI. So now we're going to look at another example. In this case, we have a perfect square that is going to take place. So for this reaction, we have carbon monoxide reacting with steam to produce carbon dioxide and hydrogen gas at 700 Kelvin. The equilibrium constant is 5.10. Calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. So we're going to do the same type of thing. The only thing that's different, you notice that it says each component, so I don't have anything with an initial concentration of 0, so we're going to have to incorporate the Q into our reaction. So first thing I need to do is set up my equation. So I would have carbon monoxide reacting with steam, so that would be a gas, steam would be a gas, it would form hydrogen gas and carbon dioxide gas. So I have a homogeneous system for this. So I have my R. I'm going to set up my Kc expression in this case. So I'd have the concentration of H2 times the concentration of CO2 over the concentration of CO and the concentration of H2O. So they tell me initially that I have 1.000 moles of each of the components. It's a 1 liter flask, so that would be the molarity for each of my initial reactants and products. So now we need to determine the direction the reaction is going to move. It tells us the Kc for the reaction is 5.10. So we're going to solve for QC. And since I have 1 for each of those values, hopefully you can see without having to plug it in your calculator that my value for Q would be 1. So now since QC is less than Kc, that tells us that we have too little product that is formed, so the reaction is going to shift to the right. So once more, I would have minus x and minus x. I'd have plus x and plus x. So my equilibrium concentration, I'd have 1.000 minus x, 1.000 minus x, 1.000 plus x, and 1.000 plus x. So if I set these up into my expression, I would have 5.10 equals 1.000 plus x times 1.000 plus x divided by 1.000 minus x and 1.000 minus x. So I can combine these and just make it a little bit easier and say that I have 1.000 plus x concentration squared divided by 1.000 minus x concentration squared. And because I have squared in both the numerator and the denominator, it will be very easy for us. I'm going to rewrite this over here so we have plenty of space. I have that concentration squared and 1.00 minus x and that concentration squared. So what we can do is just take the square root of the entire thing. When we do that, the square root of 5.1, that is equal to 2.26. And then that just gives me 1.000 plus x divided by 1.000 minus x. So I can now multiply both sides of the reaction by 1.000 minus x, and we end up with 2.26 minus 2.26x equals 1.000 plus x. So if I switch everything over to opposite sides for my reaction, I end up with, in this particular case, 1.26 equals 3.26 times x. So divide each side by 3.26 and x will equal 0.387. So now for my concentrations for the CO and the H2O, both of them again will be identical. I can take 1.000 minus that value for x, so their concentrations will end up being 0.613 molar, and the concentration of H2 will equal the concentration of CO2, and that would be 1.000 plus x. So I would have 1.387 molar for their concentrations. The next reaction we're going to look at is the decomposition of SO2Cl2 into SO2 and Cl2 gas. Suppose you start out with only reactants in a rigid container. If the initial concentration of the SO2Cl2 is 0.543 molar and 43.6% of this initial concentration remains when the system has reached equilibrium, what are the equilibrium concentrations of each gas in the system? So in this case, we're not actually having to calculate out the value for the K. We're just simply looking at the equilibrium concentrations. So for this here, we can start off. I'm going to write out a Rice table. And we will have SO2 and Cl2. My initial concentration is 0.543. So here I'd have minus x. These two would be initially 0. I would have plus x and plus x. So at equilibrium, I'd have 0.543 minus x, x, and x. So in this case, it tells us only 43.6% of this substance remains. So I'm going to take the reverse of that and figure out how much was removed. So if I take 100% minus the 43.6%, that tells me that 56.4% of the SO2Cl2 was converted into the SO2 and Cl2 gases. So I'm going to take the initial concentration, 0.543, multiply it by 0.564, and that equals 0.031 for the concentration that would be equal to x. So now I can plug it in. Both my concentration of the SO2 and the Cl2 would be equal to 0.301. And then the concentration of the SO2Cl2 would be equal to 0.543 minus x, or 0.301, which would give me 0.242 that would be remaining. Okay, so for our last problem for tonight, we are going to look at the reaction between bromine gas, Br2, and chlorine gas, Cl2, to form bromine monochloride gas, BrCl. We're going to suppose that we have 0.5 atmospheres of BrCl 0.01 atmospheres of Br2 and 0.02 atmospheres of Cl2 mixed in a container at a specific temperature. The equilibrium constant at this temperature is 550. Determine the equilibrium partial pressure of each gas. So I'm going to first start off again by setting up my Rice table. So as I set that up, I have the Br2 plus the Cl2 forming the 2BrCl once it's balanced. And now from here, I can put in my initial partial pressures. So I have an initial partial pressure of Br2 of 0.0100 atms, 0.0200 atms for the chlorine, and 0.500 atms for the BrCl. For my C, I have x, x, and 2 times x. However, this will be the unique circumstance. Unlike the other problems, if you notice, I have an initial partial pressure for each of our different substances in the chemical reaction. So we need to solve for Q to determine the direction of the shift. It tells us in the problem that the Kp for our reaction is equal to 550. So we need to solve for Qp. So to solve for Qp, I would take the partial pressure of the BrCl concentration squared divided by the partial pressure of the Br2 and the partial pressure of the Cl2. If I plug those values in, I have 0.500 atms quantity squared divided by 0.0100 atms and 0.0200 atms. And so if I multiply all of that out and divide it, I end up with a value of 1250. So in this case, my Qp is greater than my Kp, so that tells me that I have too much product and not enough reactant. So I know my reaction as a result is going to shift towards the left. So I can put a minus sign for the product BrCl, and I can put plus signs for each of the reactants Br2 and Cl2. So I can now put my equilibrium concentrations down on the bottom. I have 0.0100 plus x, I have 0.0200 plus x, and I have 0.500 minus 2x. So as I begin to set up my last problem here, I'm going to put that equal to the Kp. So I have the 550, and then I can place my concentration or partial pressure for the BrCl, 0.500 minus 2x, and that is a quantity squared. And then I have 0.0100 plus x and 0.0200 plus x. In this situation, because I have initial concentrations given for each one, doing the 5% rule is not really an option in this case. We have to do the quadratic equation to figure this out. So as we set up this expression here, I need to FOIL out my two different components. So if I have the 0.500 minus 2x times 0.500 minus 2x, that will equal 0.250 minus x and plus 4x squared. For the bottom, 0.0100 plus x times 0.0200 plus x. And I'm going to go ahead because I'm going to need to multiply both of these into both sides to get it out of the denominator. I'm going to multiply both of these times 550. So when I set up that expression, that would give me here for this part, I would have this equaling 0.11 plus 16.5x plus 550 x squared. So I can now set my two equations equal to each other and combine like terms. So I can subtract off the 4x squared from both sides. So that would leave me with 546 x squared. I can add, because this part combines together to be minus 2x. I can add 2x to both sides, which would give me plus 18.5x. And finally, I would subtract the 0.25 from each side. And when I do that, I would have minus 0.14. And I can set all of that equal to 0. So in this case, we need to plug it into our quadratic equation. Again, for that quadratic equation, remember we had the negative b plus or minus the square root of b squared minus 4ac all over 2a. Sorry, I'm not going to do the little song for you. That's the math teacher's job. So you've got that. And we have our values in this case. A equals 546, B equals 18.5, and C equals a negative 0.14. So I'm going to plug all those values into the quadratic equation, and we have two possible roots that come up. The first one is 6.5372 times 10 to the negative third. And the second root that we get is equal to a negative 0.0480. Now, obviously, I can't have a negative concentration for a problem. So when we look at that, we know we can automatically take this concentration and get rid of it. So our final answer for the change in x would be 6.5372 times 10 to the negative third. So now I can take this value and plug them into our expression. So for the concentration, or partial pressure, for the partial pressure of Br2, that would be equal to 0.0100 plus, I'm just going to write it out in its normal notation, 0.0065372. So that would equal 0.0165. Going to round there, and that will be atmospheres. I can look at the partial pressure of Cl2, which would be 0.0200 plus 0.0065372, and that will equal 0.0265 atmospheres. And then finally, for the partial pressure of the BRCl, I have 0.500 minus 2 times 0.0065372. And when we solve for that, we end up with 0.4869 atmospheres for the equilibrium concentration of BRCl. So if we were to place these concentrations back up into our expression, we should get somewhere close to the 550 for the value of the K. So this wraps up the Rice table problems. We'll work through some together in class tomorrow just to make sure that you guys have this figured out. But that wraps up this first equilibrium unit.